Hello, my name is Troy Ziliang Kang, and I am a research scientist working with Professor Giovanni Traverso at the Mackey Department and the Koch Institute of MIT. And it is my greatest pleasure to present our latest research. And thanks so much, Christine, Sarah, and Koch for giving us like this amazing opportunity to present our research. And the my research is about adhesion. And as you can see, the title is Achieving Adhesion on Complex Surfaces. So in the next several minutes, you will see a lot of like fishes. But actually, what we really want to do is trying to look at the nature and trying to get inspiration from the nature from those fishes to see if we can develop novel drug delivery like platforms that can achieve adhesion and retention in a very slippery and complex surface inside the intestinal tract, where we call as the gut. So what we draw the inspiration from is actually a very unique fish called remora. And as you can see, this remora fish has a very unique underwater mechanical adhesion strategies. So it has like a adhesive like disc on its head. And those adhesive disc is uh, composed of a lot of like tiny independent compartments. And those compartments, by just pressing it, you can achieve like a passive suction. And also on these top of those each compartment, you can see tiny spinels and lamella structures. And this can enhance the mechanical interlocking when those tiny compartments uh, adhere onto a softer surfaces. And this become the active mechanical interlocking strategies enabled by the active response of the remora fish. And what we did is actually we're leveraging like smart materials to mimic such kind of like behaviors. Another thing we want to mention is that actually the anatomic structures of different remora species, they're just so different from each other. They're involved towards their hitchhiking recipients. And you can actually get an idea of how the things looks like when we go to the next slides, because um, as we can see that the remora, they can adhere to very different kinds of surfaces, such as like a hard surfaces like the turtle's back, or very soft surfaces um, on like the skin of a manta ray. And for the first time, we did a very comprehensive mechanical and behavior studies of how remora adhering to soft substrates. And we find actually this is quite different. And if you can look at this video, you can see that when the remora fish adhere to a plastic plate, which is a hard surfaces, it's more relying on its self-sliding and frictioning to achieve the adhesion. But if the remora fish is going to adhere on a soft, like stem tissue phantom, which has a dynamic morphing and topological like differences at different like places, you can see like it will fully unfurl its adhesive disc to achieve a multi-compartmental adhesion and to press uh, as much water as possible, like when it achieves adhesion. And this really inspire us, like our strategies. And based on those understandings, actually we develop our own adhesive platforms. And as you can see, like this tiny devices is the device we developed based on the inspiration of the remora fish. And this is the second fish I'm mentioning right now. This is a goram fish. And what we did is we want to understand how our remora mimicry devices can adhere to various different kinds of surfaces and under different conditions. So we specifically tested our devices on a swimming live gourmet fish. And as you can see, this image, like which we submitted, actually relates to the surface topology of the scale of the gourmet fish. And you can see like its surface topology is very complicated, and roughness and polarimetry scanning can show like this complexity is happening at different levels in terms of its surface topology, geometry, as well as its rising of those scales at a different level. And with that, we can conclude that our device can just achieve a very strong adhesion on various different kinds of surfaces. And with that, I would like to thank the great support and guidance of my lab, the laboratory for translational engineering. This is a huge work comprised of a huge amount of contribution from different kinds of scientists from different backgrounds. And specifically, I would like to thank my advisor, Professor Giovanni Traverso, and my collaborator, Ben Mueller, who helped to just characterizing all those beautiful pictures and material characterizations. And we also like to thank the foundations who support this research, the Gates and the ARPA-H, as well as Professor Christopher Kennelly in Boston College, who helps to establish all those fish studies, and also Professor Kay Smith from New Jersey, who helps to rendering those big, great pictures for us. So that's all. Thank you so much.